I'm Jen Foster, and I'm going to be talking to you today about the article We Did Nothing Wrong, which is a look at the importance of software quality. Software is an important part of our everyday lives, right? It governs very much of what we do. We allow it to control many of the things that we use to accomplish our daily tasks. The question quickly gets highlighted, can we trust these technologies? Do we understand what they're doing? Can they cause us harm unintentionally? The key takeaway from this particular article is software, when developed well, is a great benefit to society, but ultimately software that's developed poorly or negligently can do immeasurable harm. We Can Do Nothing Wrong looks at software quality disasters, one in particular, and then provides several other examples of software that just let us down. It didn't do what it was intended to do, or it usually did what it was intended to do, but in the cases that it didn't, it caused terrible trauma and disaster. The big highlighted scenario for this particular article was Multidata's treatment planning system for the Cobalt 60. This treatment planning system was designed to be used in a specific way. It uses 4 blocks to shield the more sensitive pieces of a person's body and to guide the different beams to the appropriate place for the appropriate time to treat cancer. So this happened in Panama. The employees at National Cancer Institute in Panama were very concerned about the quality of the hardware that they were using. They had raised several concerns that they believed it wasn't safe, wasn't necessarily well maintained, and they were looking for ways to make a more safe experience for their patients. In order to do this, they found a way to run the system, the treatment planning system, which was designed for 4 blocks, and they used 5 blocks to provide more shielding for their patients. In order to do this, instead of inputting the 4 blocks independently, they basically made a conglomerate shape, and they input the dimensions of those into the system to design the treatment plan. Now, there were times when you could do that and it would be completely fine, but if you input the block dimensions in a certain way, it would cause massive overdoses for patients. At least 5 people have died specifically because of this. 28 patients were harmed, and it's hard to tell what the long-term implications are going to be for the patients that receive these massive overdoses. When you look at it, you say, how on earth did this happen? There was a study done, an investigation done into Multidata's treatment planning system, and what they recognized is that Multidata had inadequate software specifications. They didn't have proof that they had adequately tested the system. They didn't listen to consumer complaints that they had received that said that it was possible to misdose due to the way that you input the block dimensions. Additionally, manuals were incomplete. So it didn't say that you had to do the input of this stuff in a certain way, the input of the blocks in a certain way. It didn't lead you to understand that there would be bad implications. Additionally, when the software accepted bad dimensions or things input inappropriately, it generated a solution that looked correct. There was no indication that you had done anything wrong. This is sad. This was a failure on the part of Multidata to take care of the patients that it was supposed to be trying to help, but this is not unique. The Therac 25 is another cancer treatment system that was designed with both high and low energy operation modes. So you could use it for low energy. If you selected the high energy operation, it would put a plate in between you that would convert this beam into an X-ray and help to treat the patient's cancer. Now, because it could switch back and forth, you needed a user interface to be able to interact with the system. People got familiar with the way that the system operated and would be able to quickly input high or low energy operation modes. There was a case where the operator selected a mode incorrectly and were able to arrow up and change that mode of operation and go down. However, if it was done quickly, within 8 seconds, the changes were not accepted, even though the user interface indicated that they were. So what happened was, instead of this metal plate being placed in front of the beam for these high energy operation modes, it would operate as if it was a low energy operation mode, and it would massively overdose patients. How could this have happened? Well, when they did the research into what happened with the Therac 25, The code was written and tested by one person. He didn't leave adequate comments. He couldn't think outside of his box, right? So he didn't think of ways that the other users might operate the system or the failure case modes when they accidentally input the wrong mode of operation. Additionally, when this happened and patients were overdosed, the machine did shut down, but it would shut down and give a minor error code. And operators were allowed to override that error code with just the press of a button. This resulted in sometimes the machine shutting down and being restarted up to 5 times in a patient session. There were 3 deaths that were recorded from this. 2 of them were very extreme. One man lost his use of his arm, both his legs, his vocal cords were paralyzed prior to his death 5 months after radiation treatment. And in another case, within 3 weeks, a man went into a coma with a high fever of 104 and radiation burns to his brain and brainstem. You might be not as concerned about those things just because we don't all get cancer. We don't have to be treated, right? So maybe there's less of an impact because there's a smaller audience. However, there are everyday situations that happen, right? Have you been in a plane? Have you driven your car to work? Do you turn on your lights in your home? So here's some situations where things happened in more everyday situations that caused accidents and loss of life. So the Northeast power outage, there was a race condition that existed in the software that allowed an overload of the power grid without anybody knowing, right? Power lines fell into trees. This caused an overload. It should have triggered an alarm. The race condition happened and the alarm didn't get set. And the power grid was down for several days. There are 3 deaths that have been tied to this particular instance, although they believe there are several more that can't be directly attributed that are because of the power outage. General Motors had to recall several, I think 3.5 million cars because the braking distances were increased because the braking system did not understand whether you were in 2 or 4-wheel drive and didn't apply appropriate braking. Have you ever flown in a plane, right? So there's a minimum altitude warning system that alerts pilots whether they're too high or too low, or whether they're too low upon landing. In the Korean Air Flight 801 situation, they were flying into Guam, and because the software had a bug that caused faulty alarms to be set, they reduced the radius that you would receive these alarms from 54 miles to 1 mile. This resulted in a pilot flying directly into a mountain because they were too low. It's not just in civilian applications that this happens either, right? There are military applications where we see software bugs causing loss of life. We use the Patriot missile defense system to intercept missiles that are coming towards our troops. This happened, there happened to be a case where if the system was run for too long, the ranging algorithm would get off and would not be able to look for an incoming missile in the appropriate place. This happened, and several troops lost their lives because the Patriot completely missed the Scud missile that was incoming. The sad thing about this is that we had actually identified this from some information from the Israelis and had a fix on the way that arrived the day after the Scud missile hit the troops. Additionally, the Patriot missile defense system had an issue where it couldn't distinguish incoming missiles from friendly planes that were flying around the area because there's an auto mode on the Patriot missile defense system that didn't require user input. This resulted in shooting down 2 British pilots and an American pilot before it was corrected. The Osprey is a very unique helicopter/airplane where the rotors can be facing up or facing forward. There was a situation that was a combination hardware-software error where a hydraulic line broke and it took down some motors. There was a flight controls reset that needed to occur. The software involved with that flight controls reset resulted in instability in the flight control system, which resulted in a stall and this Osprey landing in a marsh and killing all 4 Marines on board. The overlying principle that we want to take from this is software quality matters. Applications need to be foolproof, and whether you think it's a large or a small application, poorly developed code can kill. This author got a panel together. They made 6 recommendations to improve software quality. They believe you need to certify programmers, much like we do our medical professionals and other people that take on life-altering obligations. We should certify our programmers so that they're prepared and qualified to do their jobs. We should certify teams. This is more corporation specific, that we should have teams that can prove that they follow healthy design, coding, and test practices. We need to check, recheck, and check again. We need to ensure that we understand user use cases and that there's not an opportunity for users to input things that will cause the software to behave unexpectedly. Raise the bar seems very clear cut. We need to implement and follow standard code conventions so that when you develop software, it's easy to understand, test, and verify. Test, retest, and establish a seal of safety. That means test early, test often. Start with unit test. Allow an independent verification team to verify your software and give you a seal of safety that says, hey, this has been thoroughly vetted and we guarantee that it's safe for use by the public. And finally, don't buy problems. If you refuse to buy software that has many bugs in it, companies will begin to implement strategies that stop producing it. The conclusion that I got from We Did Nothing Wrong is that there are not sufficient national standards for software products. Consumers deserve a product that can be used safely and effectively, and society cannot rest until the major causes of dangerous software have been remedied. In the future, I would want to do more research on the work at SCC and SEI that's looking to develop programs that reduce software defects. What can we put out to corporations to enable them to make quality software? Additionally, I'd want to investigate advocacy techniques to push nationally recognized software quality standards. I think this is somewhere where we're really lax, and there should be an opportunity to improve the quality of the software that impacts our everyday lives. Thanks for listening to my presentation. If you have any questions, feel free to type them in the discussion board and I'll respond.